Great. Pleasure to have Josef talking about machine learning and automated reasoning.
Oh, thank you. So thanks to the organizers for inviting me here. So this is a lot of stuff done with many people, but Cezary Kaliszyk sort of stands out among them as my co-author of many of these things in the last 5 years or so. So I'll try to sort of give you some high-level motivation and then examples of what we are doing, so that you can use it for your own learning and hopefully train yourself and do more of these things. So in general, you can ask questions anytime. I've given this talk too many times in a fairly high-level way, so I'm happy to focus on some of the things in a more detailed way. Like if Laura wants me to show him how the features exactly look, etc., I'm happy to do it. So this is sort of one slide about the high-level motivation, which is like pretty ambitious, like what should be the components of the ultimate system, which will automate mathematical and scientific thinking. And like, at least in my opinion, you need a lot of capabilities like pattern matching, analogy, like we were talking about it in the previous talk already, induction from examples, like this thing, which is in generally called maybe intuition. I would call it inductive thinking. Obviously, you need deductive reasoning, like without decent correct deductive reasoning, you will not finish that proof, or at least not a correct proof. And like we all know that these two things somehow go on in our minds when we try to do mathematics, and somehow that there is feedback between them. And we also use a lot of knowledge when we are doing this sort of stuff. So we have the capability to very quickly reject some idea based on a lot of previous experience, for example. So the one good corpus where at least doing this sort of AI research seems mildly plausible is this formal mathematics, these large libraries of formal proofs and theorems. And obviously today, like with the sort of general progress in AI, people are also thinking about doing this on top of totally informal corpora, like for example the stacks corpus, etc. But at least when I was thinking about this, let's say 15, 20 years ago, let's say the natural language processing methods weren't far enough to, let's say, take a huge corpus of naturally written mathematics and do some sort of fairly deductive science on top of that topic. So it seems to me that doing it in 2 steps, or today possibly, is somehow combined, and first develop like fairly good reasoning methods over totally formal math, and then try to align it with informal math is a sort of more scalable approach, perhaps still today. On Friday there was this discussion where Tim Gowers said something like, proof assistant isn't what a mathematician would think it is. It's definitely not something which would do proofs for you. And I took it as a fairly critical comment, like saying that automated theorem proving definitely isn't today something which would be in general useful to mathematicians. And then that there were other people talking about the sort of flourishing traditions, So I'm definitely on the Tim Gower side, and I think maybe linking it back to the whole historical overview which happened on Friday, I think the sorely missing point today in automatic theorem is this intuition-based methods, which at some point I think Larry was, who obviously I admire, everybody has to admire him, said something like capturing intuition is too hard for us. So let's try to do the inferencing part of the automated reasoning processes. And obviously you can do a lot of this research when you do also symmetry breaking by, I don't know, like having good orderings for equality, etc. But at some point you run out of these ideas, the theories become too complex, and like basically things today end up in a brute force search, which is totally lacking any intuition. So to give you some sort of flavor, what I would consider to be flourishing AI research today are things like this, like very recent, for example, AI beating humans in poker. Some time ago, like Watson beating humans in Jeopardy. Obviously, this one made a big splash a year ago, and this is like 10 years old when the Stanford people basically got the first breakthrough in self-driving cars. So that's what I would consider to be say flourishing automated theorem proving today. And basically all the examples which I showed you are successful because to a large extent they got some handle on what is intuition that they managed to learn. So I think we are currently still really missing that. It's interesting that like in the historical overview on Friday, we had all these people starting with Herbert Simon and over etc. But actually, I think Alan Turing was the guy who really was thinking about this in a very relevant way for today. So, as you all know, he did this paper in 1936, which is still today being interpreted as like theorem proving is being hard, or the halting problem is undecidable, etc. But he went probably through a lot of development during the hacking years where he used statistical methods. And in 1950, he basically established artificial intelligence, and he basically says there something like, we may hope that machines will eventually compete with man in all purely intellectual fields. Obviously, saying that knowing is 1936 undecidability result. And
it applies to humans as well.
I'm sorry?
Undecidability result applies to humans as well.
Yeah, and well, some people might object, right? This Penrose guy, for example. So, and he actually established, like the last chapter of his book there, of his paper, is on learning machines, where he sort of in a very visionary way says something which has been largely happening in the, like for example, the AlphaGo system, when you really train game playing engine on good human games, and then you sort of run it to against itself to self-improve, etc. So if I would be giving an historical overview relevant to automated filtering, I would definitely mention him as sort of the grandfather or godfather of what has been happening in these domains. So that's the sort of large scale motivation, and obviously like there are all these blue sky visions, like let's sort of develop strong AI by looking at these large formal libraries, but also, like, as you have seen in Jasmine talks, like people are proud that actually we can help some people at least a bit today with automation over all of these libraries, and make that formalization faster. I should say that again, like I believe that the reason why we have successfully developed reasoning over very large libraries is that we are not doing brute force search. We are doing, for example, machine learning. So this is some sort of bigger plan how this project of developing AI over large formal libraries has been attacked for some time. So we try to translate these libraries into the strong reasoning tools which we have today, and then we obviously test and evolve various AI, machine learning, and theorem proving tools for them, and then if it works too well, then obviously we produce stronger and stronger or more and more difficult benchmarks, and like we really have like dozens of benchmarks today. So now I will go through some of the tasks that are sort of strongly related to various AI and machine learning tasks. So let's say in 2002-2003, I really translated the whole Mizar library in a way that I could give it to the automated theorem provers which were available at the time. Like, just to give you an idea, the TP standard still wasn't a standard. So, for example, the translation I did was to the DFG format, which was used by the Spaß system, which was one of the best theorem provers for the particular kinds of problems. And some you could see that this is not totally possible, but you can prove quite a few of the sort of Mizar top-level lemmas and practically all of the very low-level Mizar lemmas with these automated theorem provers. But the tasks for which the ATPs were totally unprepared at the time was that when you give them something like 80,000 lemmas and ask them, please prove the next one. Eventually we started to call this task of please select from the library the set of lemmas which is as small as possible and gives the highest possible chance to the automated theorem prover. Premise selection, and obviously you could say that this is some like magic because like this is obviously some undecidable task, right? Or whatever. Like if you make it finite, then it's exponential or whatever. And the surprising thing that we know pretty well today is that this is really not something magical. The mathematical texts and these libraries of proofs behave pretty similarly to for example, natural language text in some way. Like there is a lot of repetition, there is a lot of stuff that you can learn by statistical machine learning methods, which allow you to reasonably predict when given the next conjecture the set of facts that will be useful for proving it. So already here when somebody tells you like this is a magical, totally inaccessible property of mathematicians, like we have pretty good data saying that this is in many cases not the case. So for example, this Cezary proof advisor, really like 14 years old now, is just a very simple machine learning method called naive Bayes. So that's very simple frequential statistics, where you basically take all the facts in the library. From each fact, you extract some features. In this case, just the symbols, just symbols like a plus, equality, etc. And for each of the facts, you associate to these features the set of previous lemmas which are used to prove that fact. So that would be your output labels. So for each proved lemma in your library, you will basically get one training example, associating the features and the sort of set of names of lemmas which are used to prove it. And that gives you a training set of, let's say, 50,000 examples. On that you run your favorite machine learning method. And obviously you do it in a way that you train on some data and evaluate on some other data, and you measure the performance. So if done in this sort of very simplistic way, already you get something like this. This 70% coverage of the first of the needed premises in the first 100 recommendations, in sort of your first 100 Google hits for this. And like if you use this as a very rudimentary sort of premise selector for the automated theorem provers, then at the time, like giving it to Spaß gives you something like 14% of all the theorems. So over the years, like these data are from about 3 years ago. This has been improved to about 45 to 50% on the various corpora, not just on Cezary, but on, let's say, all and Isabel, etc. I have this bet which I made 3 years ago, and I think it's pretty conservative. So if you want to bet me, you can bet me.
Josef?
Yeah.
What do you attribute the improvement?
I'm sorry.
What do you attribute that improvement to?
Yeah. So here is one picture. So for example, this shows you how the better machine learning methods much faster give you the right set of lemmas from the library. And I could show you maybe the next picture actually.
It's okay, if you're coming to it anyway, you can.
Yeah, well, yeah. So on this picture you can see that it matters. So the sooner you get the right set of lemmas, the better for you, because typically like all these guys degrade if you give them too many. Like that's currently that's in the nature of how all these guys, like not just vampire, but basically any automated theorem program currently explodes with too many of these lemmas.
You done with your answer?
Well, sort of, yeah.
Can you go back to the slide?
Yeah.
So these features look kind of weak. I mean,
Yeah, they are. Yeah. So
that's
that's
because you're using the explicit symbols and
yeah.
the explicit
Yeah.
names and so on.
Yeah.
Whereas I was actually looking for something like this pattern of theorem or
Yeah,
pattern of lemma.
So another answer to your both questions is that like you can obviously build in a lot of intelligence into how we characterize mathematical objects, right? Like what is a similarity between two statements? So basically, like nobody knows exactly, but we, for example, know that like just using symbols is worse than, for example, using all subterms, possibly with some variable matching if you are just treating them as strings, or if you, for example, characterize each formula but by the set of all terms in them, and all their unifications or all their possible generalizations, because again, that tells you like this particular subterm can be matched or unified with that particular subterm. So, or like the one thing which we do not have here is actually what I was mentioning during the previous talk, validity models. Like if you have a big set of models, like typically we use finite models because dealing with infinite models is tough. Then evaluating each formula in a well-chosen set of, let's say, 1,000 models, and using these 1,000 values as some sort of characteristic vector of characterizing this particular formula gives you a sort of totally different feature-based characterization of mathematical statements than, for example, just looking at it syntactically. Or like very recently, the Google guys took a formula to be really just a string of characters, or just a string of tokens, and then the idea is that you try to train a neural network which is recurrent, so it sort of sees the context, and you train it simultaneously with the premise selection task. So somehow this thing is called embedding. The string of characters, so the string of tokens, becomes a vector of real value, for example, 100 or 1,000 long dense vector, which is somehow magically trained using the sort of deep learning stuff to have features which are useful for premise selection, for the premise selection task. I should say that it, like we hoped that it will work, for example, reasonably well as it does, for example, in image recognition today. But at some point, you really get these sort of very high-level features there, like a prototypical cow or dog or whatever. We are not sure we are doing that at this moment. Another thing which sort of was tried there was, for example, to expand definitions. So instead of taking symbols as a opaque object, which is just a name or string, you can take the embedding for the definition of that symbol and sort of recursively unfold all the symbols using their embeddings in these formulas. And that also gives you some sort of much more semantic treatment of all the objects or all the characters and strings in your formulas, because somehow the idea is that the embeddings will encode semantics,
I
basically.
think Katya's talk was something along those lines, right?
Well, I'm not sure if Katya is doing any embeddings. Well, you can ask her. So that's sort of the digression about features. What's behind this progress? So definitely better and better focusing on the right set of lemmas helps really a lot. So to give you an idea, we can, or let's say 3-4 years ago, we could, by using all the weapons we had, and I mean something like 3 weeks of CPU time on a reasonable server, we could prove something like 40% of the Mizar theorems when given the full previous library, like in this really way when you always allow the full previous library to be taken into account. But by all sorts of cheating, we can prove something like 56%. So for example, looking really at the human written proof and trying to use it for cutting down on the set of eligible lemmas. And so now we have the set of, let's say, 30,000 Mizar lemmas, which we know how to prove by using kind of webpires, Z3, etc. And because we know the sort of ATP proof, we can minimize it. We can really exhaustively try to remove all the redundant lemmas from the proofs. And rerunning the minimized set with basically any theorem prover today gives us something like, I don't know, 95% of these proofs in very little time. So it really matters very, very significantly if you can do this guessing much better. So yeah. So anyway, this picture is just some sort of comparison of the various premise selection methods. Yeah.
Question or comment. On one hand, I agree with you that, I mean, if we could do the guessing much better, we'd have a higher success rate. But at some point, to do the guessing much better, we basically have to do the proof, and then we don't need the prover anymore, is what I would think. Or do you agree or not with that statement? I mean, if we're really, really good at guessing, I mean, at some point, the best way to guess is to actually do the proof and find it, and then you guess it right. Right? I mean, you understand what I'm saying? Does it make sense to put so much energy in relevance filter instead of the prover afterwards?
So what I said was, I'm not sure if it's in conflict with what you are saying, but what I said is that it took us like something like 1 month of CPU time on a server to get to 40%, whereas if we have it today, then we can use, let's say, 1 hour of CPU time on the same server to get, let's say, 50%. This was sort of the
No, I was thinking about your comment about 95%. I interpreted it as...
So what we have today is, let's say, 56%. Like these numbers have been changing, but
Yeah.
I'm not stating. And if I, let's say, well, 95% or 56% is a bit more than this, right? Like this is just an estimate. Like it's about like this. So this is using sort of very little search. But once you have it, once you have the relevant lemmas, like at least the Mizar proofs, but also the flat spec proofs, and I bet the Isabel proofs, go through really easily. That is something. So your question is like, when does the machine learning become so complicated that it's better to do proofs, right?
Well, something like this, or are these two different problems,
No.
or because it's,
No.
in some sense relevance filtering is about doing the proof as an abstract sloppy level. It's a
Yeah,
bit-
I agree. Like I think so. That's, by the way, one of my first points, that we should really do these sort of induction and deduction together and build systems which do them together. And for example, what worked in Subzilla quite a bit is that people run the subsolver for some time, then extract features from the partial unfinished proof runs, and that gives them a better idea of what strategies they should be running, whatever it is, Minisat with, etc. I sort of basically agree, like these things should be done together, and already like the way like systems like Malaria do them, they are done together. Like you have to finish quite a few proofs so that you can learn from them, so that you can use the learned knowledge to finish more proofs, and then again you learn from those, etc. So yeah. Okay, I'll forward. This is again another slightly oldish picture where basically you take the premise selections and you again link them to an automated theorem prover, like Vampire in this case, and you can sort of see that the better machine learning methods from the previous picture, like this MORCG, which is some kernel-based machine learning, give the theorem prover quite a better chance. But there are also some other interesting things. So for example, this sign system by Kristo Hodder wasn't really performing so well here. So you can see that here it really sucks. Whereas here the performance isn't so bad, and it, for example, at some point reaches the performance of the second best machine learning methods. So that probably tells you something about how sort of funny and wild is this domain, that you can really get many different proofs for a particular lemma, and just the fact that you memorize some proof doesn't mean that somebody can encode some sort of strategy or come up with a particular method, which in this case, for example, works quite nice for the automated theorem prover, which will produce alternative proofs.
These, did you look at how, so I assume the x-axis is n, or n best line facts?
This is the number of premises used, so you get the machine learner, and it tells you, like, this is the ranking of premises, and then we slice it at various points.
So of those, how many were actually used in proofs? You know, were they all used? Or?
Oh no.
Yeah. So wait, was there some?
Well, like the it's actually intentional. So the minimization gives you something like this. So when you when you find the proofs, you can still minimize them. And if you minimize them, it typically leads to finding the proof much faster later. So just the fact that an automated theorem brewer has found the proof using, let's say, 50 premises, doesn't mean that this is the sort of ultimate result. Like from 50 premises, you can very often go to something like 30 premises.
No, but it may be a measure on the ranking that maybe ranking could be improved to get more problems with fewer premises.
Yeah. So if you rerun this, then definitely things improve. So that really leads to the various sort of meta loops which are around this. So this is a slide which you have already seen from Jasmine. So today we believe we have something like 45% success rate on the top level lemmas, but as I said, like some of these data are quite oldish now, so we should rerun them. A very recent result of Cezary Kaliszyk and Łukasz Czajka is a useful and working hammer-fall cock. When they got something like 40% success rate on reconstruction, so they can really get the proof going through the cock kernel in 40% cases of the cock standard library. And the interesting thing about it for the constructivists among you is that they get the proofs using Vampire and Improver, etc. And they get like 50% of them, and then they lose some, but not too many, going to 40%. So this is done on the cock standard library. And obviously the challenging thing there is the translation going from cock to first order logic, and then the sort of various methods how they reconstruct the proofs. So these are the sort of high-level premise selection things. I've probably spoken about some of these things already. So for example, we have this semantic features which encode term matching and unification, which improve things quite a bit for the machine learners. A fairly simple improvement, but still giving a lot of performance, are fairly old statistical methods like this term frequency, index to term frequency, and this like semantic indexing, which from your set of sparse features create some sort of weighted, in the case of latent semantics, dense vectors, which generalize better in some sense. Cezary and Thibault Gauthier recently did this very nice work on basically statistical matching between different libraries where the concepts can have very different names, and they might not even correspond to one another exactly, but it's done on a nice statistical level when you basically abstract the symbol names from all formulas. For each symbol, you get the formulas, abstracted formulas which hold about it, and then you basically say that two symbols are similar if the set of abstracted lemmas about them have a high overlap. And then you sort of match the highest overlaps against each other, and you instantiate and you run the algorithm again. And this really allows them to import lemmas from, let's say, Hall 4 or Isabel into Hall Light and vice versa, doing some sort of super hammer where you might either trust the imported lemma or you could try to recursively through it in the imported library. We can actually also use this technology for conjecturing. So you can take just one library and find matches between different theories there, or at least syntactically different theories there. Like imagine you have multiplicative groups and additive groups in the same library. Then this sort of matching technology will allow you to transport the lemmas developed for the multiplicative groups for the additive groups, and again you can try to prove them. Lemmatization, that's a method where you don't just look at the graph of previous top-level lemmas, but you look at all the sort of low-level lemmas, which, for example, FlySpec, there is like 1 billion of those. And you do some very fast methods, like, for example, PageRank, for quickly extracting the sort of top candidates, like taking the 1 billion to something like 10 millions, and then basically doing the premise selection also with them, and that sort of augments your set of facts that you can use for proving the next things. And I already maybe the last one is interesting. So that's basically when we no longer use just the automated theorem provers, but we program the interactive theorem provers to statistically, based on the current subgoal, use an appropriate tactic with appropriate parameters. So imagine you are doing something like your whole light proof, and you run some induct tactic that leaves you with some subgoals, and then for these subgoals you sort of statistically, using in this case k-nearest neighbor, look up in a huge database of all previous subgoals which subgoals matches it best, and then you sort of try to run the tactic with the appropriate parameters from sort of those things. So this sort of high-level statistical search on the tactical level improves quite a bit also on just the sort of hardcore translation to automated theorem provers. I had mentioned this already. This is just a table if somebody is interested about how many features you can get on the Mizar library, and it's a small subset. This is like 2078 theorems selected from the Mizar library. The Mizar library itself is like 150k formulas. If you use these various feature extraction methods, so for symbols, it's not too much. Whereas if you go into some sort of terms, for example, subterms, then or these unification features, then you can get really quite a few here. But still, like the speed of the very simple machine learning algorithms like k-nearest neighbor and naive-Bayes is sort of reasonable. It's good. Low-level guidance. So obviously, because these things work for these libraries in a high-level way, I try to put them really at the core of the automated theorem provers. So Maria was saying that I'm inventing funny names. So apart from malaria, we invented also male cop and female cop. So male cop, so Jens Otten has this mean connection prover, mean cop, and it's really a surprisingly efficient connection-based prover written in a very compact way, like I don't know, 100 lines. Maybe you can. The main prolog code can be read probably on 10 lines. And it has surprisingly good performance on the first large theory benchmark, which I created in 2006. It beat Spaß, which at the time was this really C-implemented pride of the Slavic people. So we took this lingo and put again a fairly simple machine learning naive base into basically the main non-determinism point there, which is when you are extending the Tableau branch, you have some sort of tip of the branch where you can unify, let's say, with all the clauses which are in your problem. And obviously the idea would be to use the machine learning to tell which clauses you should unify this, or put some priority on that. And at the time, like this experiment, we couldn't really run it properly because the machine learning was horribly slow. It was something like 1,000 times slower than the Prolog inference engine. But if we really tried hard and just measured the abstract time, like so the number of steps it takes you to get to the proof, instead of measuring the real time, then we got on average about 20 time proof search shortening. So the sort of proof search over the 250 MPTP challenge programs was on average shortened 20 times. So we did this efficiently in 2015, creating this fairly efficient male cop or female cop, and that really showed us, like we still were quite a bit slower than the core Prolog engine, but not so much slower. I think we were like 40% slower, and we got about 15% more programs to using training on the previous programs and applying to the unsolved programs. Very recently, this is a paper this year, Michal Ferber did something even more sophisticated with this Monte Carlo connection prover with reasonable results, and currently we are doing sort of reinforcement learning on this thing.
So do you get premise selection as a side effect?
So typically, no. Typically, we don't use this. So we, for example, for Melcop, we did this on the MPTP challenge programs, but on those small versions of those programs. So we do not allow all the previous lemmas from the library. We limit it to the lemmas which we know are sufficient for the proof. Because like these things, we consider them to be sort of orthogonal, like the high level premise selection and you could also try to combine, but we didn't want to reinvent premise selection using this. Might be interesting research.
Yes. Is the time taken by the training each time? Could you persist it?
Sorry,
could you persist the information that's learned between runs? Trying to understand what the time overhead is.
Could we persist or
persist store?
Could you reuse the training results?
So we do that. So for example, for female code, it's a huge database of the decisions which you have sort of, for example, for female code we did it even for the whole Mizar library. So you get something like 15,000 problems solved by Linko. And on every decision we sort of record the decision, and then when we get a new problem, it's a pretty challenging technological issue to reduce the database to the size when it's not horribly big for guiding it on a particular. So there are actually stages to it in order to make this 1,000 and much smaller number. So again, this is Cezary's very good work on making this feasible. You can also do this for state-of-the-art situation-based systems. So this is very recent, basically last year and this year, very efficient learning-based guiding machine, or Enigma, which we now have for eProver, where we train a very fast linear classifier to sort of separate the good and the bad clauses which eProver generates. And we really compile this linear evaluator into eProver because we need it to be very, very fast. And again, like we get an immense number of negative examples, and the positive examples are the clauses which are useful for the proof. So we do the learning on that. Like in this case, it's pretty fast. It's basically just linear regression with some bells and whistles. Again, a pretty interesting thing is how do you design the features of these clauses to be reasonably quickly extractable, yet giving you a decent amount of information. And then a fairly important thing is also to combine it with the sort of more standard way how eProver evaluates clauses. So if you just do it only by machine learning, sometimes you get a very big clause evaluated as positive, which sort of, if you do it all the time, might mislead the situation prover in a horrible way. So you need to put some bounds on it by, for example, using the symbol weight, etc. So this is the first result which we got, like on the AIM programs, which is involved of long-running project. We got something like 86% more problems solved using training previous programs. So I could talk on and on, so I should stop at some point. So there are all these self-evolving meta-systems which I already mentioned. So Malaya is this systems when you solve some problems, learn from it. The learning gives you better premise selection, better sort of heuristics like Enigma inside theorem provers. So you can run it on the unsolved problems again, solve some more problems, learn from it again, etc., etc. So this gives you some sort of infinite feedback loop between the learning and the theorem proving. Then there's this blind strategy maker, which picture tells you more probably. So you want to grow a set of good and possibly fairly different ATP strategies for all these complicated theorem provers like P, for example. And so you want to do something like evolution when the strategies are like these giraffes, for example, and the problems are their food, and if the giraffe specializes better on some problems which cannot be eaten by the other ones, then obviously the giraffe is more fat and more evolved. So I'll just show you some pictures. So these are the training problems. So you use 1,000 training problems for this sort of evolutionary thing. So you start with some eProver strategies, which can solve something like 570 problems from the 1,000. And then we have like 3 versions of this blind strategy maker. This is the sort of first version. These are 2 new versions. And as they evolve and evolve and evolve, they solve more and more problems by developing the new strategies. So this was on the training program. This is comparison with on the testing programs, which there's like 400 of them, where we compare with Vampire and the outdoor schedule of eProver around, let's say, 64 seconds. And finally, well, I'm not sure if I shouldn't skip it. So I'll just tell you that one thing we are also doing using all this sort of stack of premise selection, AI, and machine learning is to try to learn the informal to formal translation when we would really, in the end, hopefully be able to understand mathematical books, for example. And the primary example was this book by Tom Hales, which really corresponds to his flyspec development, where you can really align it like this. It's probably slightly invisible. This is the informal stuff, and these are the formal light definitions which you can sort of align it to. And then we do basically statistical natural language processing, like doing some sort of reasonable parsing of the two things, and in the end, like we obviously train it on the aligned corpus of the informal and the formal formulas, and the system which we have. Yeah, I can actually show you the demo is doing something like this. So you type in a reasonably informal formula, then you run on it the sort of statistically trained parser on the thousands of previous disambiguated examples. Then you sort of type check it using the Holite type checking procedures. The things which go through the type checker are given to the holy hammer, to the sort of big hammer we are developing for flyspec. And some of the parsers can be easily disproved, like you can prove the negation basically, like the first one. And here you can see that the second one is the one which can really be proved using quite easily using some known theorems in the Holite library. But you also really have like all these other disambiguation, which, for example, this C sign is just a complex version of sign, and this CX is the casting of the real number to this complex version. So you can also understand it like this, for example. So the ordering is by the sort of statistical relevance. Yeah.
When it says no advice, means that the investment.
The whole hammer is too stupid.
But it seems that
doesn't
the
know.
example you have here
Mhm.
is the real version from another one, which is just lifted to complex, and then there's a no advice.
Don't ask me why is whole hammer stupid. It's artificial intelligence.
The three of the no advisors should have been disproved, but the last one should. Yes.
Oh, if obviously we are doing it with pretty small resources, so I think we are giving it like 10 seconds for each of these guys, and like the 10 seconds are distributed into I don't know how many strategies and theorem tours, etc. So like if we throw more resources into it, something which you consider as obvious should probably be proven or disproved, but I cannot guarantee this is. We have some funny examples actually. I think there might be something like possibly this one. So this one was it? Yeah, maybe this. Yeah, so you can understand. Not sure. Oh yeah. So this minus minus x equals x, you can obviously understand you using many possible interpretations of minus minus, like a vector or a matrix, etc. So here it turns out John has formalized it for square matrices, and there is the theorem about it, matrix knick-knack. But you can also prove it for rectangular matrices. And he doesn't have the statement in the library. So actually our falsification and then disambiguation procedure in this case behaves like a conjecture, because it took a statement which was formulated too non-generally, too specifically. Then it falsified it, and then after the disambiguation, we actually get the generalization to the rectangular matrices, which takes longer to prove because the library theorem isn't there. So after John saw this, he actually added it to the library from well informed. Anyway, I should be finished. So there is lots of challenges, and we all know them, so I will dwell on them. There is a growing number of people involved in all of this. So the people in Prague, in Innsbruck, all sorts of ATP, ITP people in Nijmegen, people at Google, and more, and there are various finding agencies, etc. So if you are interested, then this is the conference to go to. We will be organizing it in France, French Alps, next March. It will be the third issue of that conference. And also, if you are very interested, feel free to visit us in Prague and work with us on this sort of stuff. Thank you. Yeah.
So you do your experiments on libraries that already have all been formally proved, right? So when I do formalization, generally what I discover is I need lemmas that are not there, and then I add them. But when you then say, okay, my system is very successful, it has all the lemmas it needs available already. So
I'm not saying something like that.
what?
I'm not saying that.
You say 40%, 50%, 56%, and so on.
Yeah.
So finding out what the lemmas are that you should need.
Yeah.
This kind of machine learning fuzziness might make that harder, maybe.
This is very interesting. So we do this conjecturing stuff using all sorts of techniques. And the main technique which we are currently trying is this sort of statistical alignment. So once you have seen a theorem done from your multiplicative groups, you will sort of know how to do it for your additive groups. So that's the idea. We did the statistical analogies. They are often very imprecise, and often they help you. So Thibault has recently tried to train it on a database of whole four theorems, like this number of whole four theorems, using this big training set and this big evaluation set. And then he just by this sort of conjecturing procedure, he gets, I think, like 200, like 390 out of 735. Do not exactly know what is this graph. So I agree with you that speculating the right lemmas for a theorem which is too far away is definitely, at least today, one of the main tasks we should be attacking.
So I think I'm with Jasmin in this, that basically to find out what lemmas are unique, you shouldn't speculate, you should just do the proof and find out where you get stuck. So not just randomly start generating interesting lemmas because they might be useful, but more like, okay, follow the logic of the proof heuristically for a while. And, apparently I need this.
We obviously try to do that. Like the methods how to do that are not there yet. So like I'm not going to tell you that we have solved this, because if we have solved this, we could do Fermat's last theorem, etc.
Well, as you know, I'm more a user of proof of systems, and I have a naive question. So suppose I want to use an automation tool based on this kind of AI method. And so I'm setting a lemma, which I consider fairly easy, but I'm too lazy to prove it. So I guess this would be the case. I would be tempted to try this kind of method. And then the tactic fails. What am I supposed to do? Should I run it again with a different configuration? Should I prove it manually and declare that it's not provable by outcome? There's something I'm missing here. On the workflow that.
So the sort of classical workflow is this sort of sledgehammer workflow, where Larry toiled quite a bit to port Joe Hurt's Mattis into Isabel to have it reasonably reconstructed in Isabel.
But I have maybe the wrong feeling that for automated decision procedures, I can have a very rough idea that okay, it's a linear algebra fragment plus some.
So that is sort of.
If it fails, maybe.
I would definitely for things where you need induction, where you need decision procedure. Like I think the way how we just did it with tactical, when you are a reasonably big class of problems, which are reasonably uniformly discharged with some fairly similar sequences of tactic invocations. I think learning statistical tactical search is definitely going to be good for you. Like that's sort of my understanding.
Maybe I can add something because I'm both developer and user of Sledgehammer. So, and the short answer is yes, we try Sledgehammer for 30 seconds or how much time patients would have, and if it fails, we start the kind of ease our proof with several steps, and then we recursively call Sledgehammer, and then we go as deep or as shallow. So I remember at one point I had and usually after you use it for some time, I mean at some point I was able to predict. I was like, okay, this will take 2 seconds, this will take 20 seconds, and it will time out. And I got very good at my predictions. But once to the point where I could even stop calling Sledgehammer and waiting, I mean, I just shot it in my head. And
You should
train your personal network.
Have the system advise you.
Sledgehammer learned how to do.
But anyway, it was,
So the machine is training you.
right. And so I mean, so when I'm saying if you can bring only one tool with you on an island, it shouldn't be Sledgehammer, because that tool either succeeds or fails. And same thing with any of those tools. I think that Josef is like Polyhammer and so on. I mean, you really get nothing back when it fails, and you have to be ready to do a manual proof. Nonetheless, it still saves you a lot of work. And we also have measurements out in the wild, like the SEL4 people, like we measured for 6 months on 20 machines, like how often they were calling Sledgehammer and what's the success rate and so on. And it was about 40%, so like out in the wild. So they counted,
My feeling was just that it was harder to predict when it would fail.
Yeah, it is
more
harder,
AI you have, the less
it is harder, but I mean,
predictable it gets to. I mean, I was really surprised with that example. It was like, there was one statement in the real numbers was okay and almost instantaneous.
Yeah.
And then you lift it to the complex number, like syntactically, and it fails.
Well, it depends on the lemmas you
Sure,
have.
of course. But then
It's random.
It's not random, but it's pretty random.
So
I think somebody should be deciding the order.
Yeah, great. Okay. Oh, sorry, he had his hand up a long time ago.
okay.
Okay. Do you see a difference between various areas of mathematics or computer science here? Have you done statistics? Where are you best?
I think the most statistics was shown by Jasmine in his talk, like then the Sledgehammer machine learning paper really has the various things going from probability theory to some sort of hardcore computer science, whatever it is, some protocols and Jinja, etc. So I think one but again, Jasmine is here. I'm mostly interested in mathematics, so I'm not. I mean, I'm happy if we can help computer scientists, but I think the general idea which I'm getting from those evaluations is that SMT solvers like C4, for example, Z3, are sort of getting better and better on the sort of more computer science parts, whereas on the mathematical parts, you still have quite a bit of quantification, etc. So the sort of traditional superposition-based automated theorem provers are still better. Somebody already said that the proofs in CS are sort of much more shallow and boring, and the formulas are long because you need to encode the full memory model of something, and that's horrible. Whereas in math, the statements are short and the proofs are long, etc.
So where does FlySpec fall in that?
Oh, FlySpec is interesting because we do the evaluation mostly only on the textual part. If we took into account the sort of computational part of FlySpec, then the numbers would be very, very different. But for example, the nonlinear equations for FlySpec, that's like 6,000 of CPU hours, whereas the textual part is like 2 hours, 2 CPU hours. So all this sort of machine learning would be very, very different if we took into account the nonlinear equations, for example, for FlySpec.
So,
Sorry, Fred, I'll come to you.
No,
so I guess regarding Ashley's question, like, can you report to the user in any useful manner information about your partial search which was terminated because you ran out of time?
Mhm.
I think there was another talk which discussed like lemma selection for user-facing purposes.
So I like long time ago, I did this Cezary Proof Advisor where I said, like, okay, I'm getting something like 14% here. That's not very useful. So let's just give to the Cezary users the most relevant lemmas, which will tell them, like, these are the things you might be doing at this current point of proof. And I honestly do not know why they didn't use it. Like, I think it sort of was useful to me at least. But the one or two Cezary users, which I got at the time, told me later that really combining it with the APP search, which tells you these are the 8 lemmas and the proof follows from them, is much nicer information for them than just these 10 lemmas might be useful for you. But it could be like some sort of HCI issue, like maybe I should have visualized the lemmas better or whatever. I don't know. Like we still, like what Katja was saying, that they cannot evaluate the stuff. Like this stuff definitely can be evaluated in the sort of machine learning way. You sort of look at the coverage of how many good hints you have, and you can improve on the machine learning side, etc. So I personally think that sort of this sort of Google for a formalizer should be a useful thing, regardless of whether you actually improve the thing or you don't. But, well, this is my one experience.
But I mean, you could look at the outputs of a saturation-based theorem prover, and very often it might have derived clauses that have just one literal, and you could speculate those as conjectures and negation of those as conjectures. So an example I had recently, which I found very frustrating, is I had this goal, looked at it in Isabel, and I thought, okay, Sledgehammer will do it. It failed. Then I zoomed it, broke it down, and there was always one goal that failed. Broke it down, all the way down to if you apply this, if you convert a set to multiset, and the multiset back to a set is the identity. And then Sledgehammer was failing even on that. And I couldn't get counterexamples, but it turned out there was one. If you take an infinite set, the multisets of Isabelle are finite. And it's not reflected in the name of the data structure, just to confuse you. So I spent 1 hour, zooming in and so on. Whereas Jamal could have told me, oh, if you can prove that the set is finite, then I can offer you this proof. And then I would have realized, oh, I forgot the finite assumption. And my set was finite, right? Of course. So I really wasted 1 hour, and if you had the tool, possibly based on machine learning, because these provers generate tons of clauses. You don't know which one is the right one.
The machine learning is called Bill-McCune or Bobberov currently.
But
They look at
finite
the
is a
output
common
and-
one, and it's an assumption we often, don't need very hard machine learning to discover that if you derive a clause of the form not finite, blah, 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 maybe this is what you should prove next. Right.
We were talking last year at the ITP about how Bill McCune would recognize when a situation-based proof goes wrong or goes well, etc. And Bobberov is similar, like he can tell you this is no good, you should stop it, etc. Like, there definitely is some machine learning to be done.
Right. That was my question.
Okay, so let me ask the last question. So you started the talk by saying, you want to get somehow intuition automated. And, the results you're getting are, in metric terms quite good. But are you making a dent on intuition?
I'm sorry?
How are you doing with intuition?
You mean how far is it to human intuition? Or I would say sometimes it does surprising things. I'm happy that it at least does this sort of premise selection reasonably. The recent thing with tactic-toe.
No, but you're still talking in terms of metrics when you say that. Not, talking in terms of,
You mean how do we measure that we are close to human intuition?
Yeah.
Oh, good question. I think for that we should eventually do the informal to formal bridge and start really looking at the informal topics. I think.
but is it possible that, because you're using the corpora that may have lots of ugly proofs in them, that you're learning stuff that isn't,
Bad habits.
that from bad data you learn.
Yeah, we definitely from bad data we can learn bad theorem proving. From good data we can prove good theorem proving. That's definitely one of the experiences. And we can combine them in various ways, so you can never say that one is totally bad and one is totally good.
Okay, with that, let's thank you.